Nuclear power has in its short history developed a very different approach to safety, at least with respect to design, than that used in aviation. In addition to the general safety engineering problems of all new and potentially dangerous technologies, the nuclear power industry has a relatively unique problem with public relations and has had to put a great deal of energy into convincing government regulators and the public that the plants are safe in order to get approval to build and operate them. This requirement, in turn, has resulted in a greater emphasis on probabilistic methods of risk assessment. The time required for empirical evaluation and measurement of safety is orders of magnitude greater than is practical. Another result is that nuclear engineering has, until recently, used a few designs for which a lot of past experience can be accumulated and has been very conservative about introducing new technology, such as digital systems. That conservatism, however, is giving way to greatly increased use of digital instrumentation and control and other new technology. In an effort to promote the development of nuclear power in its early days, and also because the hazards were only partly understood, the industry was exempted from the requirements of full third-party insurance in some countries, such as the Price-Anderson Act in the United States. Instead, government regulation and certification was substituted as a means of enforcing safety practices in the industry. The first nuclear power plant designs and sizes were also limited, although this has changed somewhat over the years as confidence in the designs and protection mechanisms has grown. The primary approach to safety in the nuclear industry is defense in depth. Defense in depth includes page 277. A succession of barriers to a propagation of malfunctions, including the fuel itself, the cladding in which the fuel is contained, the closed reactor coolant system, the reactor vessel, any additional biological shield such as concrete, and the containment building, usually including elaborate spray and filter systems. Primary engineered safety features to prevent any adverse consequences in the event of a malfunction. Careful design and construction, involving review and licensing. In many stages, training and licensing of operating personnel assurance that ultimate safety does not depend on correct personnel conduct in case of an accident. Secondary safety measures designed to mitigate the consequences of conceivable accidents. Oversight of operations and licensee event reports. Licensing is based on identification of the hazards, designed to control these hazards under normal circumstances, and backup or shutdown systems that function in abnormal circumstances to further control the hazards. Most of the emphasis with respect to safety is placed on the shutdown system that is brought into operation if a hazard occurs. The backup system designs are based on the use of multiple independent barriers, a high degree of single element integrity for passive features, and the provision that no single failure of any active component will disable any barrier. Note that setting nuclear power plants in remote locations is a form of barrier in which the separation is enforced by physical isolation. Because of the difficulty in isolating plants, emergency planning has gotten more attention since the 3 Mile Island and other early nuclear power plant accidents. The dependence on defense in depth using barriers and reversion to a safe state, which does not usually exist in aviation and other fields, is unique to nuclear power. While specific details may differ between countries, redundancy and high integrity paths are commonly used. and engineers have emphasized high component reliability and protection against component failure. Such component failures can lead to failed barriers and inability to reach a safe state. Because many people outside the United States are most familiar with nuclear power as the most common, highly safety critical industry in their region, there have sometimes been assumptions that this is the only approach to safety engineering, but the design and general safety engineering approaches used in aerospace and defense are very different. Using the nuclear power defense in-depth approach to safety, an accident requires a disturbance in the process, a protection system that fails, and inadequate or failed physical barriers. These events are assumed to be statistically independent because of differences in the underlying physical principles. A very low calculated probability of an accident can be obtained as a result of the independence assumption. This assumption is debatable, however. Recovery after a problem has occurred depends on the reliability and availability of the shutdown systems and the physical barriers. A major emphasis in building such systems, then, is on how to increase this reliability, usually through redundancy of some sort. The certification of nuclear power plants has emphasized probabilistic risk assessment that includes estimating the reliability of the barriers and protection systems. Because empirical measurement of probability is not practical for nuclear power designs. Most approaches build a model of accident events and construct an analytical risk assessment based on the model. Such models include the events leading up to an uncontrolled release, as well as data on factors relating to the potential consequences of the release, such as weather conditions and population density. With the increasing use of non-stochastic components, such as computers and digital systems in nuclear power plants, such probabilistic assessments may have decreasing relevance. In addition to probabilistic risk assessment in certification of nuclear plants, operational concerns are addressed through extensive incident and error reporting, an emphasis on creating a strong safety culture, external oversight, and regulation.